So, welcome back. As we discussed, we will talk about governing equations. These governing equations will essentially describe, are basically used for describing the entire flow field for any combustion process. Okay. So, as we will see that, or as you can anticipate, that these governing equations comes from basically conservation principles: conservation of mass, conservation of momentum, conservation of scalars, conservation of energy. Okay. So, basically all these conservation principles and how generation of something leads to the depletion of that one, or generation and depletion of these quantities, and how that affects can couple with the flow field, etc., that we will see. Basically, we will see that this conservation of mass is essentially is coupling between we will see that it's basically involves density and velocity. The conservation of momentum once again involves density, velocity, and pressure. Okay, because essentially the pressure gradients is the characteristic force here, and that will cause acceleration or deceleration in a flow, and as well as this the frictional loss due to the presence of viscosity. Then we will see that how species can be advected, how particular species can be advected along with the flow, and how it can diffuse from a region of high concentration to a region of low concentration, and how also it can be it can be generated or depleted because of the source terms which comes from the chemical reaction rates. And the conservation of this energy, that is which will start with the internal energy form, and then we will go into the enthalpy form, and then we can show that we can arrive at a temperature form, and we will also see that how this enthalpy can be transported with the flow, and then it can be also there can be pressure that can affect the enthalpy, the time variation of pressure, and then also there can be like conduction processes, heat conduction processes, as well as enthalpy transport due to the different diffusion velocities, and also how enthalpy, how the enthalpy of formation essentially gets converted into sensible enthalpy through the heat release term inside the energy equation. So, these governing equations are very pivotal, are central to your understanding of the flow processes inside a combustor, because it is using these governing equations we actually plug in our understanding of kinetics, our understanding of transport, our understanding of convection. All these things come into, are basically assembled using these governing equations. So, with these governing equations, of course, in a discretized, when you do a discretization, and then in a grid you can actually solve using CFD, computational fluid dynamic techniques, to solve the flow inside actual combustor also. So, either you are doing theory, or you are doing experiments, or you are doing CFD, you must know the governing equations and understand what each term represents. Okay. So, first we will do this with the we will do this control volume derivations, and then we will also, for different things like mass, momentum, and energy, we will go to this conserved scalar formulation, and then these two things, this reaction sheet formulation and the simplified one dimensional numbers, we will go into in a later stage when we will go into look into the actual flames. So, as we said that chemically reacting flows. Okay. Now, combustion is of course a very solid example of a chemically reacting flow. So, chemically reacting flows are governed by conservation laws for mass, momentum, energy, and concentration of individual species. All right. So, the conservation laws are derived keeping in mind the continuum hypothesis. Of course, you know about the continuum, that is when you look into a small part inside the flow, you still find density to be uniform inside a very small part of the flow, and it does not happen, does not show discrete jumps due to presence of one molecule and then nothing and then one molecule. So, it is nothing like that. So, the continuum hypothesis is certainly preserved in these cases. All right. So, one can define density as a continuous variable, which is mass per unit volume, and then the governing equations model the multi-component reacting flow with a set of partial differential equations. So, we will start with integral equations and then we will move on to partial differential equations, and along with the governing partial differential equation, the constitutive and auxiliary relations are required to form a set of closed equations. So, the conservation laws that we will use, that this does not close the problem, this will only give rise to this partial differential equations, but to close this partial differential equations we will need this constitutive and auxiliary relations. And of course, as you will see that these equations will be very complex in their full forms, and we will appropriately simplify them under suitable assumptions. All right. So, the central theorem that we use for understanding the conservation laws in fluids is the Reynolds transport theorem. Okay. Now, this Reynolds transport theorem is very central because it allows us to use our knowledge of conservation laws for a system to a control volume. That is, to give you an example, suppose this is my control volume, this is my, this red boundary is my control surface, and then there is a packet of fluid which is this is a system which is moving. So, say this packet of fluid was at this position at time t minus delta t, this occupies inside of the control volume at t, and then this packet moves out at time t plus delta t. Now, what I want to say is that the law that you know, the laws of physics, say like the Newton's law or the mass conservation that you know, is for this packet, okay, of fluid which is moving. The mass of it is not changing, the momentum of this, if there is no external force, it is not changing, and this energy, if there is no external supply of energy or loss of energy, that is also not changing. But that is not what we are interested. Okay. We are interested in applying this law inside a control volume. Why? Because your energy, suppose your engine is actually a control volume, right. So, you are not interested in the mass of packet of mass that goes in at different state and this that goes out. We are interested in what happens inside this control volume. So, first we need to understand the law that will translate the conservation laws from the system to the control volume. So, what does it say? It says that of course, we can go this in details, but this is not a fluid mechanics class or a thermodynamics class. So, we will just leave it here itself. It says that the time rate of change of an extensive property xi, okay. Please note that this is the time rate of change of the extensive property xi, okay, which is within a system, is essentially equal to the time rate of change of xi within the control volume and the flow rate of xi across the control surface. So, of course, when you are moving a packet of this fluid, there is no inlet or outlet, but in this control volume that you have defined, okay, in this thing there is continuous inlet and this is continuous outlet. So, it says that it is the time rate of change of xi that is happening inside this control volume, and that amount of xi that comes in and that amount of xi that has gone out, the difference between them. So, that also you need to take care of. Okay. So, that is the basic essence of Reynolds transport theorem, and here we use this extensive fluid property xi. Capital Xi is nothing but capital Xi is equal to integral small xi dv. That is, so this xi is equal to integral v xi small xi dv, where v is the volume of the control volume in this, when it is capital V in this manner. Okay. But you have to be careful, sometimes we will use v as velocity also. So, please be careful with that. So, this says that this d xi dt, that is the total derivative of this property xi following it in a system sense, is essentially is equal to dou xi dou t integral over xi dv, that is integral over the control volume, plus the integral over the surface xi times v vector dot n ds, v vector dot n cap ds, whereas n is essentially the surface normal. So, this part, this v vector dot n ds basically characterizes the mass flow rate that is happening, and also this multiplying with xi gives us the flow rate of the property xi that is happening. All right. If this is a moving control volume, then this essentially becomes v relative So that is the velocity, actual velocity minus the velocity of the control volume. So this is the Reynolds transport theorem, and then using this, which is defined over the entire surface, you can convert this surface integral into a volume integral using Gauss divergence theorem. So which is given this. So once you have converted it, you see that that basically this is also a volume integral, this is also a volume integral. So we can write that using this, you can write that d xi dt is equal to integral v times dou xi dou t plus divergence of xi v vector integrated over the entire control volume. Okay. So this is the basic formula for going from a system representation to a control volume representation. This is for a system, that is the rate of change of property xi for when you are following that packet, when you are following that system. Okay. By system we mean that there which does not, through which there is no mass flow rate that is happening. So when you are following the packet of fluid, the rate of change of that of xi on that packet is given by this, but when that packet passes through a control volume, this is given by this volume integral. Okay. So this is how you basically connect. So essentially this is the rate of change of xi of the connection happens, that this is the rate of change of xi happening inside that packet of fluid when it is residing inside the control volume, and that must be equal to the rate of change of the property xi when it is within the control volume plus the flow rate of xi that is happening across the control surface. Okay. So this is how you connect. So integral of v is nothing but this dou xi dou t plus divergence of rho divergence over xi times v vector dv. So now this xi is essentially a generalized property, but we can use this for any property, and we will use this to basically derive the basically change the representation of the xi. Sometimes we will consider xi as mass, sometimes we will consider xi as momentum, sometimes we will consider xi as a mass of certain species, certain kind, and then sometimes we will consider xi as the total energy. And by changing this representation of xi, as we did before also for deriving the transport properties, we will arrive at the conservation laws of essentially mass, momentum, species and energy. So now first we need to understand that this we need to understand the concepts of the definitions of the velocities, because here as you know, combustion, the difference between combustion and other and fluid mechanics, because here we not only involve reactions but we also involve multiple species, it is not one kind of a fluid. So Vi is the velocity of the ith species. Okay. The small vi, and this average, this small v is the mass weighted bulk fluid velocity. So this v is essentially the velocity that we are familiar with, right. So this is the mass weighted bulk fluid velocity with which the entire fluid is moving. Vi is the velocity of the average of the ith species, with is the velocity with which the ith species is moving. Okay. So summation rho I vi is equal to rho v. So rho I vi is nothing but the partial density. Okay. And we will see that how rho I is defined is nothing but yi, that is the mass fraction is essentially rho I divided by rho. Partial density means the mass of the species I divided by the total volume, whereas the density is the mass of the full thing of the entire all the components divided by total volume, right. Whereas this vi is the molecular diffusion velocity, which is nothing but capital, which this represented by capital Vi is nothing but this velocity of the ith species minus the bulk velocity, mass weighted bulk velocity. Okay. So consequently it can be shown that summation rho I capital Vi is equal to essentially rho I Vi summation rho I Vi minus rho V. Okay. Why this is so? Because if we consider this thing, summation I rho I Vi vector is equal to if you start with let's start with Vi vector is equal to Vi vector minus V vector. So let's multiply both sides with rho I, and then you sum over it, sum it. Okay. So then what we will get is that the summation rho I Vi vector is equal to, this stays as is, summation rho I Vi vector minus, when you this does not contain I, so you only sum over rho I. Summation rho I is nothing but rho, so this is equal to rho v, but as we have seen here that summation rho I vi is equal to rho v. So these two are essentially equal and this becomes equal to 0. Alright. So also this vi is so using this formula and this formula, we can find out the actual v velocity is essentially nothing but summation rho I yi vi. Yi is the mass fraction, okay, and also we can show that using this, because this is equal to 0, you just divide both sides by rho and you get both sides by dividing by rho, you get yi, and you get summation yi vi is nothing but equal to 0. So these are some of the important definitions of velocities that we will use. Okay. Now please understand the difference between these three velocities. This is the velocity of the ith species, okay. This is the mass weighted bulk fluid velocity, and this vi is the molecular diffusion velocity, which is nothing but the difference between the velocity of the ith species and the bulk fluid velocity, okay. So that is the molecular diffusion velocity, and none of these will be actually equal to 0 in a given scenario, in a particular case inside of, say, a flame or something like that. Now how do you now also, if you remember, now you considered that we derived this formula, that is d xi, rate of change of this property xi, capital Xi, in the system, which is just inside the control volume, is given by v dou xi dou t, right, plus divergence of xi v vector. This v is the bulk fluid velocity dv, this v is volume, okay. So this is what we have got, okay. Now so the rate of from Reynolds transport theorem, we can say that the rate of change of mass just by changing with from the property xi to property mass. So if you now write that this xi is this xi, we say that this was equal to xi dv. So we can write m, we can basically change the representation of xi to mass, we can say m is equal to essentially rho dv, and then we can write the Reynolds transport theorem for this full thing, and that we will see if as nothing but so instead of capital Xi we have replaced with m, we replace capital Xi with m, and we see that this is nothing but integral of volume d partial d rho partial dt plus divergence of rho v integrated over dv. So now we know that total mass is conserved when there is chemical reaction. So of course this dm dt, there cannot be no rate of change of mass possible, and then this thing is possible, this thing is equal to 0, and then this becomes equal to 0. So that is what you get. So if the integral, and this be because this dv is essentially arbitrary, so we can remove the integral sign, we can remove this dv and remove this integral sign. So what we will get is nothing but this inside this d partial d rho partial dt plus divergence of rho v is equal to 0. Alright. So just to recap what we did, because this is so important, that is how we can understand the other things. So we just I will just repeat again. So we just applied the Reynolds transport theorem, d xi dt is equal to integral v del xi dt plus divergence of xi v vector times dv, okay. And now if we write that xi is equal to m, then it means that this implies that small xi is nothing but rho, because capital Xi is equal to integral xi dv. So by obviously we then small xi is equal to rho, and then we can say that dou m dou dV, and since this is arbitrary, we can remove the integral sign and we can convert this integral equation to this partial differential equation, which is nothing but partial d rho partial dt plus divergence of rho v vector, and that must be equal to 0 because there is no rate of change of no mass change is possible. So, this is our continuity equation. Okay. So, similarly we can apply the Reynolds transport theorem to derive the species transport equation, momentum equation, and energy conservation equation. So, all this we will just derive right now. So, similarly just we derived mi, we wrote that xi I is equal to mi, we can write xi is capital Xi is equal to mi, and then it means that small xi is nothing but rho I, that is the partial density of the species I, and then we can write d mi dt is equal to integral dv integral over v partial d rho I partial dt plus divergence of rho I total bulk velocity times dv. Now, please note that this is a bulk velocity, but now interestingly this is not for the total mass. So, of course, the total mass is conserved, but in this case there can be sources and sinks of dmi dt, that is the mass of a particular species need not the rate of change of the mass of a particular species inside a combustion environment, of course, may not be 0. Suppose this mi is represented by the methane fuel, right. So, of course, before and after combustion or in as the flow is happening, if you have suppose there is a flow and there is a flame, right, this is the flame you have, and suppose mi or rho I will be large here if say I is equal to mass of say like m of CH4 will be very large here, but that will be equal to 0. There will be no mass of CH4 here, right. So, of course, there will be we need to find out some sources and sinks, and those sources and sinks basically is one is a volumetric which comes from reaction, that is this is given by this rho I dV. This is equal to given by this Wi dV. Wi is nothing but the reaction rate that we have learnt, but it's in a it's a different units. We will come to that. It's actually in units of in units of mass. So, this is different. This is slightly just very slightly different from the reaction rate that we have seen. Whereas this surface we will also see that. That there can be also surface fluxes, especially from the diffusion flux Vi, and that can be given by the diffusion velocity capital Vi, and that will be given by this integral over the surface with a minus sign given by rho I times Vi vector dot n ds vector. Vi vector is the species diffusion velocity, okay. And now this since this Vi vector dot n vector is essentially 0, which are which it represents loss, and hence we have the negative sign because that contributes to the to make it as a source term, and that to represent that the flux is coming inside from outside, okay. So, as a result, this will be what we can write is that, so this is the equation, but this is not equal to 0, but instead it is this equation is nothing but minus integral of rho I Vi vector dot n vector times ds plus integral Wi dV. Of course, you can now convert this ds, this control integral over the surface to a control volume, okay, and this is now then it is now balanced. So, what I want to say is that the rate of change of mi inside the system which is resident inside this control volume. So, as a result, this rate of change of this mi inside the control volume is given by this two things, that is number one, there can be a species flux which is the flux of species carried by this molecular diffusion velocity, and also it can change due to the reaction rate that is happening inside, which is volumetric in nature, happening inside the control volume. So these two contributors will now balance the this rate of change of the mass of the species I inside the control volume. And when you apply the Gauss's divergence theorem onto this and convert this to a volume integral, you can basically transport it into this direction, into the left hand side, and as a result you can write the simplified equation, which is partial d rho I partial dt plus divergence of rho I times this is the bulk velocity and this is the diffusion velocity. All right. So, and this is essentially is equal to the, and this is of course after you have removed the integral and just gone into the partial differential equation form, and this is given by the reaction rate Wi, and which is in a this is of course in a mass form. So this Wi is also in a mass form, units of mass essentially, not in units of mass but units of mass per grams per cubic meter second. That is typically the unit of this one. Okay. And this can be of course true for any species Y. So thus what we see is that essentially this is our species balance equation. Okay. It looks simplified, but actually it is not, because we have not specified anything about this species diffusion velocity, and we will need this some constitutive relations for this rho Vi to be supplemented to close this equation, because we have not specified anything about this. And of course we will use our knowledge of chemical kinetics that we have studied in sufficient details to use this to model to basically to describe this the term, which is basically the rate at which the species I changes because of the chemical reactions. Okay. So this is the source term in the species equation. Now we can also use the conservation of momentum. Now instead xi is equal to, we write is equal to the momentum, okay, which is m times velocity. So this m is essentially m times v. Okay. And now then becomes then the partial, then small xi, which is the this was the extensive property, this is the intensive property, this is essentially a specific property. Then small xi essentially becomes equal to rho times velocity, and then the rate of change of momentum inside this is essentially integral of we just replace this thing into the, we just replace the small xi in this, and we get that it's essentially partial d rho v dt plus divergence of rho v vector over this. Now of course there can be forces acting on this control volume, and there can be surface forces in terms of like stress and pressure, and this capital P is essentially a full surface force tensor, and it will contains all sorts of force from pressure to different viscous stresses, etc. And there can also be a volumetric source like a body force Fi, though this will not be of our interest mainly in this course, which comes from this Fi, but we will keep in this one for generality. This will be of course very important, because as we will see later, all this this will contain both a pressure component as well as the viscous components, and this viscosity will actually come into this. So this is the form that once we convert this volume with this integral form to a partial differential equation form, what we get is nothing but this partial d rho dt, which is the transient term. Then we get this advective term. Both are actually both are nothing but this in this form is nothing but the acceleration of the fluid, and this acceleration is caused by this surface by the gradient of this pressure tensor, which is nothing but the force. Okay. And this force can also be exerted by a volumetric source in form of body force, and this is in another form. This we have to get the total dv dt, which is the total acceleration, is given by the minus gradient of p pressure tensor, which is nothing but the total force and plus the body force. Okay. And we will later break this up into the actual pressure and the viscous forces, and we will eventually neglect this. Finally, the conservation of energy. Now, this is the most actually this is the most complex equation, and this is also the most important when it comes to combustion, because in combustion temperature is the king, right, and essentially we will see later that from this energy we will derive a useful form for temperature. So, this transport of temperature or this transport of thermal energy will be coming from this conservation equation. So, for now we start with a very modestly we write this extensive property, that is capital Xi is the total energy, which is the total internal energy, and then the corresponding specific property small Xi becomes density times the specific internal energy plus this is the kinetic energy component rho v square by E. So, this is the internal energy and this is the kinetic energy component. Okay. So, once again proceeding similarly, we can actually by Reynolds transport theorem the rate of change of this total internal energy inside the system, which is resident inside the control volume, is equal to the rate of change of this internal energy inside the control volume, and that happens due to the rate of change of that property inside the control volume plus the fluxes of this property that is coming through the control surfaces. So, this is the control rate of change of the property inside the control volume. This is the flux of that of the internal energy plus the kinetic energy that is coming from the surfaces. Surface integral converted into volume integral using the Gauss's divergence theorem, and so this is the left hand side. This is how the rate of change, but that is we also need sources and sinks, because there will definitely be sources and sinks, because there can be an energy flux q vector. Okay. There can be a heat flux vector, and that will actually in the volumetric form appear, though it is actually in the surface form in this form q vector dot it is a heat, we can consider this as essentially a heat flux vector dot normal vector in the surface integral, which becomes essentially equal to the divergence of heat flux vector in the volume integral. And then there can also be surface stresses, which is, if you remember, flow work, that is the work done by pushing due to pushing the fluid because of the external surface forces like pressure. So, to account for that we need to, that will come into this, and this is that form. And also there can be volumetric sources or or body forces which can also come in, which can do some work, and by the body forces, and this is also come. This will typically once again will not be important in this thing, and will not consider this much. But all these things will be very important and will form an integral part of our integral, meaning very important part of our analysis here. So, if you write this thing down, this the total thing, this is the essentially the, though it is the RHS here, it actually when you write down the governing equation, this forms the LHS. Okay, and this plus this forms the RHS right hand side, this forms the left hand side, this forms the right hand side. So, if you collect this and if you collect this, what you get is, this is your transient term d rho times internal energy, specific internal energy plus kinetic energy by v square by 2 partial dt plus this advective term, this divergence of rho velocity vector times specific internal energy plus v square by 2. This can be totally written in this totally material derivative format, that is rho times total derivatives of E plus v square by 2 divided by dt. Then that is equal to the sources and sinks. This is the surface flux of heat that can come in, and that is given by divergence of q vector, heat flux vector, and then there can be this flow work, which is basically the work done by the external surface forces by pushing the fluid in. And then there can be this force due to then this can be the work by the body forces. As we said, that this will not be of importance, and we will not consider this, because we will not really consider body forces, we will not even consider gravity in this, mostly in these things. So though gravity can be important because of the buoyancy effects, but especially when you talk about fires, but in terms of this combustion course we will not consider also much gravity, and acceleration due to gravity we will not consider, and we will not consider any body forces as such, though they can be important in certain circumstances like electromagnetic, ionic winds, etc. If you do plasma assisted combustion, these sort of forces might become important, but for this course we will not consider this. Our equations will essentially be restricted to this part only. Okay. So now if we summarize, so starting from a very generalized Reynolds transport theorem for any property capital Xi, and we started with the notion that capital Xi is essentially an extensive property of a system, and which the system is essentially coincident inside a control volume, and then we can write our laws for that system, and then we can write our laws for the control volume, and it's a Reynolds transport theorem that equates these two laws by additionally considering, in addition to considering what happens, the rate of change of the control volume, we additionally consider what comes in and what goes out of the control volume, the flux of those properties, and then this flux of these properties actually come in surface form, and then we converted this surface actually as surface integrals, then we converted the surface integrals into volume integrals using Gauss's divergence theorem, and then we applied this for a generalized volume, and we applied this for mass, we applied this for species, we applied this for momentum. For mass there is no balance extra source sink required, because the mass is essentially equal to the rate of change of mass inside the system coincident with the control volume, and the rate of change of the mass in the control volume plus the mass flux coming in and the mass flux going out, that is equal to 0. So we do not need additional source sink terms. But when it comes to things like species, okay, when it comes to things like species, we need additional sources and sinks. There can be sources of sinks in terms of this reaction which can generate or deplete a particular species, and also there can be species flux coming in crossing the control surface, and we need to account for that. Momentum also, the rate of change of momentum is given by this rho dV dt, and then that can be changed by surface forces through pressure, and the gradient of pressure, and also by body forces. Once again, this is not important, we will not consider this, we will not consider this. And also in terms of energy, we will see that the rate to total internal energy, specific internal energy, that will be changed. Here we actually can do some take the dot product of this momentum equation and subtract with this this equation, and we can arrive at a energy equation for purely for specific internal energy, and that is what we have done here. And we will see that we arrive at this form, divergence of this heat flux vector times P tensor contracted twice with divergence of V, and this and then we can neglect this body force term. So this is what we have done. So now we have this complete conservation equations ready. Alright, we have conservation equations for continuity, we have conservation equation of species, we have conservation equation of species, we have conservation equation of momentum, we have conservation of energy. That is all the conservation equations we need. But then these equations are not complete, and these forms it will not be able to solve them. Why? Because you see that there are very interesting things which we do not know. We do not know about how this Vi will look like. We have equations for V, we have equation for the bulk velocity, but we do not have an equation for Vi, which is the species diffusion velocity. Similarly, we do not have any constitutive relation for pressure. Okay, we need to supply that. What can be that? Can be so this, you can think that this Vi can be supplied this by fixed diffusion law. This pressure, this can be come from this equation of state, and this heat flux vector, this divergence of Q, that can have many things, like it can have heat conduction, Fourier's law of heat conduction. It can have like your radiation source, and it can have also heat flux due to different heat contents of different species. We will see that. Alright, and also very importantly, what we need is that we need to close this, we need a constitutive relation for this omega, this Wi, but of course we know Wi, we can use this law of mass action that we have learned in the previous classes, and also we can use this the k that comes in front of this products of species raised to the stoichiometric exponents, and then we can use them to basically come at a reaction rate for Wi. So, we'll come at this, we'll come to this. So, these conservation equations are to be supplemented by specification of the diffusion velocity capital Vi, the pressure tensor capital P, and the heat flux vector Q, and of course the reaction rate Wi. And we will supplement these things. We will come at this specific closures or this auxiliary equations or this constitutive relations for these quantities in next class. So, thank you very much.